All right, for section 11.2, I'm going to break this into a two-part video. So we're going to take a look now. We're going to transition from sequences to series. So if we have a sequence, again, the notation for that will just be in parentheses or the set brackets a sub n. We can investigate the sum of the terms in the sequence. So adding a sub 1 plus a sub 2, so on. And we can write this using sigma notation. So it would be the summation as n goes from 1 to infinity of a sub n. And this is called a series or an infinite series. All right, so let's consider the sequence. We'll start with something very basic. Let's look at 1, 2, 3, 4, 5, and so on. This can lead to a series. One plus 2 plus 3 plus 4 plus 5, and so on. Which if we keep adding these terms, it's just going to keep increasing without bounds, so it will lead to infinity. So now arises this question, is it possible to add an infinite number of terms and get a finite number? So let's take a look. Let's consider this series here where we start with 1/2 plus 1/4 plus 1/8 plus 1/16, and so on. So we could write this as the summation as n goes from 1 to infinity of 1 over 2 to the n. All of the denominators are powers of 2. So now let's let S equal this series, the sum of the series here. And then let's just do an algebraic manipulation to both sides. Let's double both sides. So then 2s is going to equal, if I double the 1/2, that's 1, double the 1/4, double the 1/8, double the 1/16, and so on. So guess what? It seems now like it just shifted. So all of this right here is still s. That's what we had above. So we could subtract that. We could say now 2s minus s is just going to leave us with a 1 over here on the right side. And when we combine like terms, we just get s is equal to 1. And so we were able to do that. So we would say hence the sum as n goes from 1 to infinity of 1 over 2 to the n is going to give us 1. Pretty neat. All right, let's take a look at a definition. Given the series, which will be denoted by the summation as n goes from 1 to infinity of a sub n, we're going to let s sub n denote its nth partial sum. So then S sub n is going to equal, or we could sort of start and stop this. So now we're going to say I goes from 1 to n rather than from n to infinity, because this is a partial sum of a sub I. So now this becomes a sub 1 plus all of these terms up to a sub n. So that's how we would denote an nth partial sum. Right, so if the sequence, and again, it's important to know when we're talking about a sequence, so that's just a comma separated list there. So if the sequence S sub n, meaning we're no longer adding these, we're just looking at the terms themselves, is convergent, and the limit as n approaches infinity of S sub n is equal to some value S, so it's equal to a value which means it exists as a real number, then the series is also convergent. So we could always go back to limits to help us figure out if a series is convergent. So this number, S, is called the sum of the series. Otherwise, the series is called divergent. And again, we can always look at the sequence of the partial sums to get results. All right, so in this example, let's calculate the sum of the series whose partial sum is given. All right, so again, we would say that this sum, this summation, or again, the notation for the series, can be calculated by taking the limit of this partial sum as n goes to infinity. So this is just the limit as n goes to infinity of n squared minus 1 over 4n squared plus 1. So now we have to go back to all those limit laws, those limit at infinities here. So we did an example like this for section 11.1 where we're going to divide everything by the greatest power of n, which is going to be n squared. So now this turns into the limit as n approaches infinity. N squared divided by n squared is 1. Then we'll get minus 1 over n squared. Then we'll have a 4 plus 1 over n squared. So as n keeps increasing without bound, these fractions are going to 0, and we're left with 1/4. Now also remember too, if we're ever facing an indeterminate form, we could still go back to L'Hopital's rule where we would take the derivative of the numerator and denominator. I think there's one example like that in WebAssign. All right, now let's take a look at geometric series. So if we have a series actually it's not of a sub n, it's a times r to the n minus 1. That denotes a geometric series. And what this means is we start with a, because if n is 1, we'll get r to the 0, which is just 1. Then we get plus a times r, because that'll be 2 minus 1, which is just 1, plus a times r squared, plus a times r cubed. Now these like to kind of present themselves as fractions a lot of the time, so just be aware. So now we could say, then s, let's let s equal this whole thing here, so a plus a times r plus a times r squared. But we're going to stop this here. We'll take it to a times r to the n minus 1. Now my little algebraic manipulation here is I'm going to multiply both sides by r. So if I do r times s, then I multiply all these terms by r. So now I get a times r. And then the second term becomes ar squared. Then I get an ar cubed. And then all the way down the line, and if I multiply this by an r, this is just going to become a times r to the n. So all of these terms look like they match starting right here to here, because what's right in front, let me actually write this here. The term before this last one would become a times r to the n minus 1, and then plus a times r to the n. So all of this is right here. So what I'm going to do now is subtract. So this would just give me s minus rs, and then I would be left with, actually it starts here and matches everything above. So I'm still going to be left with a, and I'm still subtracting, so then at the very end we'll be left with minus a times r to the n. I'm going to factor an s out, and that's going to leave me with a 1 minus r. I'm going to factor an a out, and that's going to leave me with a 1 minus r to the n. And this is the formula. If you ever came across this in a high school class or previous algebra class, the summation or the sum of a geometric series is equal to a times the quantity 1 minus r to the n over 1 minus r. So a very important formula here. This is the sum of a geometric series. Now there's some clues about this that can help us determine if the series is going to be convergent or divergent. So we'll say if the absolute value of r is less than 1, and the sum is equal to a over 1 minus r as n approaches infinity. Because as n increases without bound, r to the n heads towards 0, because remember r is less than 1, so r is a fraction. So if we look up here and we see a fraction that's raised to a power that keeps increasing, then this whole part is going to turn to 0, and then we're just left with 8 times 1 up here, so that's where we get a over 1 minus r. Some other little rules or little tricks to determining what's taking place with this series. If the absolute value of r is greater than 1, the series is divergent. If r is equal to 1, divergent. And if r is equal to negative 1, divergent as well. So we'll just kind of restate this. So we'll say the geometric series denoted by the summation as n goes from 1 to infinity of a times r to the n minus 1, which is equal to a plus a times r plus a times r squared, is convergent if the absolute value of r is less than 1, and it's equal to, so the sum is actually equal to a over 1 minus r, again, if absolute value of r is less than 1. we could sort of summarize all the divergent rules into one statement. So if the absolute value of r is greater than or equal to 1, the geometric series is divergent. All right, we'll take a look at 2 examples, and then that will wrap up part 1 of this section. Let's find the sum of this series. Three minus 3/5 plus 3/25 minus 3 over 125 plus 3 over 625, and then it keeps going. So we have to figure out, this is a geometric series. We have to sort of be able to write this as a summation. So sometimes we need to kind of break this apart. So obviously we've got 3 as our first term. And then if we think that that first term is usually going to be a, because remember that we have a, then we have plus a times r. So I'm going to factor out a 3, because notice all of these have 3's in common, so this will become a 1/5. And then plus 3 times 1/25 minus 3 times 1 over 125, and so on, plus 3 times 1 over 625, and it keeps going. Now remember, it's r squared and then r cubed, so now we can say that this is 3 minus 3 times 1/5 to the first plus 3 times 1/5 squared minus 3 times 1/5 cubed. So does that look like we're getting those values? And then this would be plus 3 times 1/5 to the fourth, and so on. So in this case, a is going to be 3. Now it's alternating, so before we figure out what r is, let's go ahead and write the summation here. So we get the summation as n goes from 1 to infinity. A is 3, and then we are going to have 1/5. Remember, it's always r to the n minus 1, but we need this to be an alternating series here, just like a sequence. We need that -1, but it needs to be to the same power, to the n minus 1. And we can combine these two. So now we get the summation as n goes from 1 to infinity of 3. Because these have the same powers, I can multiply this together, so it's -1/5 to the n minus 1. So now r is equal to -1/5. So now to figure out this sum, we go back to the rules. So we're going to take the absolute value of r, which becomes 1/5, and that's less than 1. So if we go back to our rules, if the absolute value of r is less than 1, we'll figure out the sum using this, and then we know that our series will be convergent. So then the sum is equal to a over 1 minus r, which becomes 3 over 1 minus -1/5, which becomes 3 over 5/5 plus 1/5, so we get 6/5, which is the same as saying 3 times 5/6. So we get 5 over 2, 5/2. And again, this is called an alternating series. Alternating because of the signs. So let's try one more. And here we're just going to answer convergent or divergent. Here we've got 10 minus 2 plus 0.4 minus 0.08, and then so on. So again, we want to try to rewrite this so we could clearly see a obviously is going to be our first term. So we could write this as 10, and then it's going to be minus 10, and then the r has to get us back to 2. So let's say I know if I need a 2 here, it's going to be a fraction. So 10 times 2/10 will just leave me with a 2. And then we'll say plus 10. And then we could write this as 4 over, I know this is 4/10, but I need there to still be a 10, once I multiply by 10, I still need a 10 in the denominator, so we'll say 10 squared. So that will still give me, the 10s will divide out, and I still have 4 tenths. Then let's say it's minus 10 times, and I could say this is 8 over 10 cubed, because if I multiply this together, I really get 8 over 10 squared, which is 0.08. So we keep going like this. Now let's try to simplify this a little further, and that's based off of this 2 tenths. So I could really say this is 1/5. Now this is really 4 over 100, so 4 over 100 turns into 1 over 25, so that looks good. That looks like it's 1/5 squared. Minus 10, and this is really 8 over 1,000, which turns into 1 over 125. So we're looking at r to be a 1/5 again, maybe a negative 1/5. We'll take a look, and that'll keep going. So again, here we're going to have summation as n goes from 1 to infinity. A is 10. Because we are alternating, we'll still say r is negative 1/5, so then we'll get negative 1/5 to the n minus 1. And our sum becomes a, which is 10, over 1 minus a negative 1/5. So like the last problem, this time we'll get 10 over 6/5. So we multiply 10 by 5/6, so we'll get 56, which is 25 thirds.